Hi, good morning, everyone. It's Ali Rasek. I am instructing Civil 459 for University of Victoria, and today is June 11th. I just added a microphone so that the quality of my voice is better. I think generally the voice picked up by laptop is poorer quality, and I was realizing that when I randomly checked some of the recordings from previous sessions. So hopefully you hear me better and the recording quality would be even better. We are at about 21 learners or 20 learners and me. We can get started. This is again, as usual, the course outline. And yeah, we had the shake table test last week, and we completed almost until the end of module number 4. I know that last time in UVic, I ran through number 3 and number 4 as if I was presenting for a conference, but it's good that we are almost progressing according to our schedule, which is finishing number 4 until last week. However, at some point I will get back slightly, maybe not today, but in the next few sessions, I will get back to the shake table. Armando had sent me some results, and I think he shared it with everyone in the class. And one more time, we walked through the comparison of modeling versus analysis reality, so that everybody, all of us are even more confident that the analysis and engineering is valuable. It replicates the reality of the world around us. Now, yeah, today we will continue with module number 5, which is about earthquakes. Probably today and Friday, we focus on earthquakes, high-level understanding of earthquakes, before about next week, we move on to, NBCC and good stuff there. All right. I know that you guys submitted your final work plan, and we will mark it for you. All of them look good. When the draft, they looked very good, better than last year. Therefore, yeah, don't wait for us. Just proceed with your work and do whatever you promised, study, research, computer analysis, Excel, whatever you want to do, and prepare the draft report. And we didn't say it here, but I would say it's as if you are showing 60 to 70% progress on about June 28, when you submit your draft report. So it doesn't need to be complete, but it should be like you should have touched your most important promises and progressed well. And still you will have 2 more weeks to really get to your final report. Then after that, everybody or teams, they can prepare presentation to present by the end of the term, which is again in person at UVic campus. Thanks again. I think good majority attended the class. On last Friday, I didn't really use the paper to note down who was attending, so because it was good attendance. And some students, learners told me that they had some appointments, etc., which happens all the time. So generally, we are good in terms of attending. However, when we get more into engineering, we will have some quizzes as well. Engineering, I mean, National Building Code of Canada. We will have a few more quizzes because that's what you should be like. We covered a lot of theories of dynamics of structures and high level look at the procedures last week, response evaluation, today earthquakes, which some people might say not really 100% related to structural engineers, but something that all of us structural engineers, we should be high level aware of earthquakes and what do we mean by earthquakes that we use for our work analysis or design. And starting from maybe about next week, we will be more useful engineering stuff. Eventually, everything is useful, but more hands-on engineering stuff. And I expect people to be able to replicate those and use NVCC, etc. And we will have a few tests accordingly. Quizzes, like short quizzes, just to see if you guys can find something quickly in your copy of NVCC, etc. Yeah, so that's the progress. That's where we are at. And I'm happy that nobody's objecting to the sound quality. So it looks like you are hearing me. I'm using a new microphone here. Now we proceed to the earthquakes. Now, yeah, so this week we want to just gain understanding of seismic hazard and seismology, again, on the high level, as far as a structural engineer should be aware of. I assume that most of you guys want to have a career in structural engineering. Questions? Yeah, you right now or at any moment, you can just raise your hand or open your mic and just question from now, previous sessions. We are always open to that. Now jumping into seismic hazard. So the goal of our work as earthquake engineers, earthquake structural engineers, is to just gain understanding of what happens during an earthquake and after an earthquake. So this is in terms of like the economy and the socio-economic losses during an earthquake. We should be aware, like when we want to know what are the earthquake losses, we should be aware of the seismic hazard, meaning what will happen, how strong the earthquake would be felt at the location of interest. Maybe like the earthquake center is here, location of interest is slightly away. What is the inventory? What are the basically structures that are around? Highways, buildings, dams, bridges, etc. And what is the vulnerability like? What earthquake will cause damage? And last week we talked about the three levels that we studied, at least three levels. I know that different books change it slightly. Maybe some say 4, some say 2, but the way we presented it, 3 levels of, say, engineering judgment or assessment of the structure in terms of serviceability, meaning that is the structure fully serviceable after earthquake, like as if nothing has happened, earthquake comes, some shaking, and then after that we continue with our life, or the bridge continues taking vehicles, the dam continues with gate operation and producing electricity and water. So that's serviceability. Damage control means that there are some structural damages, but the whole of the structure looks pretty good. So there you see a big crack in the concrete beam and additional rotation in steel beam or column, but generally looks good. However, because say that a structure has moved as a permanent movement, that the steel member has moved too much, then serviceability is not really full. Say in building, the residents get worried, or if you have a dam, you cannot, while the dam is really sustaining the water, but you cannot open the gate and you have to like stop electricity production because you are not confident about your uh, pen stocks and everything else, but still the damage is under control. And the third level is collapse prevention, while you are borderline collapse, almost like worried that you can say 5 minutes from now everything will fall on me, so I have 5 minutes to run away and sustain my life. So collapse prevention is like slightly before full collapse. That at least the picture that I have. And this vulnerability curve, what is telling us is vertically probability of failure between 0% and 100%. One means 100%. And what PGA in that region. So peak ground acceleration, what is the maximum acceleration of the ground? You will see this notion often in quick engineering. And a lot of times we just present it in terms of G, which is the gravity. So how does the horizontal acceleration compare with gravity? Say in this case, in this typical case, if the acceleration becomes 20% of gravity, 20% of the structures, almost 20% of structures hit the serviceability limit, like 20% of the structures won't be serviceable anymore. Almost maybe one or two structure will hit the damage control limit, meaning that just a few structures will have like big rotation in the steel frames or visible cracks in concrete members. And almost no structure will hit, or zero structure will hit collapse prevention limit. So there is no worries about collapses. That's the typical vulnerability that maybe an economist will provide. Now, yeah, focusing on structural and civil engineering generally, direct and indirect earthquake effects. There are some direct and some indirect effects after earthquake or during earthquake. The direct ones are more of concern to civil engineering profession and structural generally, because while I have narrowed down the structure here, I think, and I assume most jurisdictions think, that the structural engineer is in charge of the stability of the structure. That's my way of thinking, and I think that's probably because I have seen it in different books or jurisdictions. Therefore, generally, like I cannot say all my beams and columns were strong, but my structure slided on the ground. That's, and blame it on geotech. That's my responsibility to make sure that the ground also withstand. So I put my structure on top of the ground, but kind of it's my responsibility to talk to my geotech engineer and make sure that on the level underneath ground is also safe during earthquake and after earthquake. So you guys are being trained to be structural. Don't overlook this or say it's somebody else's responsibility. Maybe these guys can say they are responsible, like geotechs can say they are responsible up to ground level, but we cannot say. We cannot say that. We should be aware of the results or output that the geotechs provide, because we put our structure on top of the ground, so we should be confident about where we put our structure. In a way, we are responsible. The ground effects of earthquake are shaking of the ground, some cracking might happen, lurching might be an outcome. Differential settlement, that's one thing that we are normally, like structural engineers, building structural engineers, they think about it, that different locations might move differently. Maybe you have different types of layers on two sides of your building and one column moves more than the other column. Liquefaction, we should be aware of that. We should avoid building our buildings on locations where there is soil liquefaction probability, meaning that soil liquefaction is like, I think, one of the top soil weaknesses, where during an earthquake or after an earthquake, soil will behave as if it's liquid, as if it's water, like its behavior would be similar to water during earthquake. And you can imagine that, like, you have built your building on top of a soil, but during earthquake, it's as if your structure is floating on water or liquid. Therefore, you should be aware of that, question that, and avoid it for most major structures. If it's inevitable, then you should ask your earthquake engineers to do thorough study and basically estimate the level of liquefaction and think about remedies as well, how to prevent liquefaction. There is lateral spreading, landslides sometimes happen, rock falls if you are by the hill or something, so you should be aware of those. And then ask your geotech engineer to estimate it or prevent it or have remedies for that. Then there are structural effects that are direct responsibility of us structural engineers. What level of vibrations will happen in the structure, falling objects, the other objects that are secondary structures or secondary members attached to the structure. We will have a discussion about them in NBCC starting from about next week. Then the damage, we talked about it, and collapse, we talked about it, so we should be aware of both of them. There are some indirect effects as well, like earthquake happens and causes landslides, tsunami, seashell, I think it's called seashell, avalanche, rock falls, etc., or even causes flood because a dam is broken, fires. Historically, we know about earthquakes that correlated with fire, especially when there's a lot of, like here, there are a lot of wood buildings and toxic contamination. Yeah, because like a place where they keep toxic material is basically damaged or cracked, etc. Again, back to earthquake effects, typical damage to building structures. I have also noted failure modes a lot of times, especially when we are dealing with peculiar structures such as dams. We should be, first of all, we should think about the failure modes. Sometimes you think it's second nature to a structural engineer, he or she, because of training and a school, they should know all failure modes and they just jump into designing for that. But for all structures, and especially for structures which are slightly unusual, the engineer should first think about the failure modes, like what can go wrong in my structure. And because of the training that they have received, they can guess well, but they should really think carefully about it and talk at different levels to make sure that within a structure, they understand the failure modes. So in a building structure, say this has two columns for masonry type or concrete type structures, for steel, dominantly steel structures, which is also composite is part of that. So the failure could be at the structural element, beam, column, etc. It can be at connection level. In steel, we also have bracing. Bracing could be damaged. And again, connection, obviously. Instead of bracing in masonry, we have walls and infills that provide lateral support for the structure. We should be aware of that. And foundation level, as I said, while we can delegate it to geotechs, but we should be high level aware of that, what may go wrong with the rock foundation. Or actually we call the concrete foundation as well. So there is a concrete foundation that we design and then rock foundation where the structure sits on it. So both of them, we should be careful with it. And frame issues that we will talk more about or a few times later on. Say general structural level issues like soft and weak stories, excessive deformations in one drift, basically in one story level, distress in diaphragms and connectors of the slabs, ponding, probably meaning that two structures hit each other, rocking, like the whole structure just lifts up on one side. On the other side, it can be even imagine building that happens to building. Rocking might happen. The structure, including the concrete foundation, starts rocking. Uplifting, water might go under your foundation and causes uplifting and reduce stability. And parapet falling, like even the fact that they may fall on some people and hurt them or damage property, economic issues causing by fall of stuff. So we get into that when we are talking about the secondary structures. And I have listed, you guys have probably taken courses in concrete and steel design, and you must or you should know what may go wrong in each structural member and how to design for that. But I would even suggest that always when you want to design some structure, even write it on paper. That I think in this structure, maybe the columns crack and the connections don't work. But it's also second nature to us structural engineers. In dam engineering or specialized buildings, we really note them down, that what are the failure modes and what we think may go wrong with the dam during an earthquake. And then you can think about that because the structure is damaged, the lifeline might be damaged as well. Highways are important and railways because they bring goods and stuff and food to a region. So you think, that's like I, as a structural engineer, think in terms of a beam that is broken, but maybe that's part of a railway that brings in food to a region. Gas and electric power could be damaged, and that's the lights. So they may be issues. Water and waste system are important to the modern life. And the communication system, maybe the mobile towers are broken, etc. So for each one of these items, we have basically listed a few things. If later on you are, as a structural engineer, join highways and department of some company or government, you know what may happen. Bending and shear failure of reinforced concrete, local and overall buckling of steel and concrete piers in bridges, pounding and unsitting and the seat locations. That's unsitting is very important for bridge design. I briefly worked as a bridge engineer, so designing of sitting is important of the superstructure, the way superstructure sits on bearings and columns. Cracks may happen, and if it's a railway, the rail itself might bend or rupture. So the structural engineer working on highways should be aware of such failure modes. Similarly, for gas and electric power, things may go wrong, rupture in the network, brittle fracture to porcelain components, like that's part of the electrical system. They have some porcelain components. Now there's a lot of good opportunities in transmission and distribution, even for a structural engineer. So just, just think carefully about these things, that why you might be needed as a structural engineer working on transmission and distribution, and as a good structural engineer who understands earthquake. There are damages to switching systems and cranes and tanks, disruptions of electric power supply, and fires and explosions. Water and waste system, they're always very important. There are good opportunities in this area as well, in infrastructure. People want to get into infrastructure as, again, structure earthquake engineers. We are worried about breakage of pipelines, slushing in storage tanks, which may cause damage, shell buckling in metal tanks, elephant foot, I don't even know what it is. You guys can do the research. Cracks that happen, and malfunctioning of the equipment. Communication systems these days, it's like a modern thing, but we are all too attached to it. Electric switching systems might damage phone lines, and also the cell phone towers, they can be damaged. And computer networks may go down. Your social media might not work, and everybody gets upset. Computer networks and transmission towers. So I read them one by one. I really like you guys to have attention on this. Those are like the different job opportunities that you will have, and you should know why earthquake engineering is important in each one of them. Earthquake effects in terms of toll. So this one just try to compare the deaths that might caused by different effects. I don't know about the region, probably it was from something in North America. Looks like flood was the most damaging, and earthquake came in second in terms of death caused by natural hazard. So that's good to have that knowledge. Financial losses, I think in this region, buildings, most of the buildings are well built, so we should be show attention to financial losses as well. Although, I mean, I said well built in terms of saving human being, which is super important, but then second would be financial loss. So in different countries, just examples shown in this table, and different countries with different GDP, or they have called it GNP, gross national product, or we normally call it gross domestic product. And one earthquake, how much damage has caused. Like you see in the first one in Nicaragua, about 40% of GNP was lost because of an earthquake. So the financial loss could be substantiated. And Guatemala, Romania. So in Romania, we also see a higher number. And so in Italy, which is G7, still we could see a 7% loss. So even in the G7 countries could be substantiated. And other examples, 30% in El Salvador. So yeah, losing money is also important. We should be aware of that. Now, yeah, some pictures of seismic hazard and issues that we should be aware of become second nature to us based on the historic experiences. This was, I think this was an earthquake in California in 1983. And as you see, there have been damages to the building. Like this building is probably not livable, but everything has held up well. That's the top goal of us as structural engineers, that we want collapse prevention. We want everything to hold up so that the people can evacuate. That's a top issue that we think about. But maybe the structure becomes unlivable, and maybe it needs a lot of spending money, like economy class that we talked about, so that the building becomes livable again. But that's also another task that we have to prevent financial loss. This is Kobe, Japan, 1995. I still remember there was huge discussion about this earthquake. You see, it caused collapse of an elevated highway. This earthquake had a vertical component. I think that was one of the first cases where the earthquake engineering industry or community started thinking about vertical effects. And in their design, yeah, they hadn't, I mean, Japanese do the best job in earthquake engineering, but apparently they were not very worried about the vertical earthquake effects. And lessons learned was, yeah, just be very careful with the vertical component of earthquake. This one was only one example, yeah. So this one is two examples, one in Japan and one in Chile, where apparently the water 2011 in Japan and 2010 in Chile, where looks like the level of tsunami happened. The right one, obviously tsunami happened, and the water was risen so that even this, whatever it is, ferry or whatever it is, hit the buildings. So another issue to be very careful about. Generally, we should be less worried in BC because the tsunami zone of BC, which is west side of Vancouver Island, and we have been there as tourists, and you see that it's very, very underpopulated. So there is less worry, at least for us. And then Vancouver is protected by the island, and Victoria is kind of protected by the island against tsunami. Most of the higher population cities by the coast are protected from the ocean and tsunami. But historically, we know that huge tsunami has happened in BC, maybe or exactly at 1700. That's what I know. So it's like major tsunami may happen here. There are look at those locations that might see tsunami on west side of island are clearly marked and warnings are given. And I don't know if I forgot whether that was the case in the island or island is too underpopulated. But in some regions in west coast of US, there are like speakers where will give warning to everyone to run away as soon as possible. Our radio stations will warn everyone in the tsunami area to run away. So luckily we have a lot of land here, so we didn't have to, like Japanese, they have shortage of land, so they should build everywhere. But we could have a safe distance from tsunami zone in BC. Seismic hazard as far as the landsliding and the liquefaction is considered. 2001 in El Salvador. I think this one. Yes, marked it. So this is El Salvador. This is Japan. This is famous that soil liquefaction caused the whole building to collapse. And here that's where it might be controversial, but yeah, so I would say it's a structural engineer's responsibility as well. Although it looks like the structural engineer has done a good job and the structure has held together, but they should also be aware of what is underneath and ask careful questions about the possibility of liquefaction. Obviously, in 1964, there was not much awareness about liquefaction issues, but now there is a lot of awareness about that. And in El Salvador, a landslide happens that endangered the life of people here. So again, a structural engineer should ask questions like, are we sure that the soil on this side will not fall on my structure? And ask us that question from your geotech. Again, more pictures of historically important hazard. The 2010 Christchurch was also an important earthquake in New Zealand. It caused a lot of damage. And when we talked about the secondary structures and equipment inside the building, you should imagine this picture like after the earthquake. Maybe looks like this building or a structure hold together, but everything inside flied. On one hand, more importantly, endangers the life of people inside. Secondly, it could be huge financial damage, like the value of this damaged secondary property stuff inside that could be huge. So we have good reasons to basically anchor a lot of stuff inside a building and make sure that everything is well attached. Similarly, in Chile, primary structure, which is columns, they have held on very well. They were designed well. That's very good. However, the movements cause the walls to break. They have caused like hazard, like probably somebody in this car was hurt or people inside. So we shouldn't really say primary structure is well designed and we are confident, because the other non-structural parts might cause a lot of issues financially and in terms of life. Yeah, last year I added this few slides because last year the earthquakes, the twin earthquakes happened in Turkey, and I attended a few presentations and I picked up some of the pictures from those presentations. So these are 2023 earthquakes in Turkey, eastern side of Turkey. And so February 6th, two consequent earthquakes happened, one with a strength of 7.7 and the second one 7.6, so both of them were strong. There was a reconnaissance report by SETIN and IGACH that probably I downloaded that and I used that. I borrowed those pictures from them. The two earthquakes were only 9 hours apart. And so this earthquake, at least for me, beside the fact that there were a lot of damage and life loss, brought awareness to the challenge of twin earthquakes. I think, as I recollect, Christchurch had the same issue. Like normally a lot of earthquake engineering philosophy is based on a single earthquake, a strong earthquake. And when two earthquakes happens one after the other, some of the philosophy that we will discuss a lot will become questionable. Like We provide ductility, and ductility, a lot of times we think of it as a fuse. When a strong earthquake happens, that fuse in a way goes off and prevents damage to primary structure, the main vertical load carrying system, which is very important, prevents collapse. However, something that we think less of is that, okay, what if two earthquakes happens and the second one is strong and happens 9 hours later? In which case, the fuses has gone off and they were used, the ductility capacity has been used. And when the second earthquake happens, we have a more rigid structure which will absorb more force and slightly damage, which is less strong. So that twin strong earthquakes, those are important issue to think about as well. There were fault ruptures that we can see here, and the railroad has moved slightly. This right-hand side one shows the road has moved quite a bit. And even on the snow, and the fresh snow, we can see marks that show, and the fence has moved. So say here you have the fence, I think it was straight line, and now you see huge movement, huge fault movement or movement caused by fault rupture. And then that's the rest of it. Supposedly before earthquake, it was like a straight line. That fence was pretty straight between the two properties. Similarly, yeah, so discussing the characteristics of these two earthquakes and how it compares with the design code in Turkey. A station means that where they were measured, so that has a number just showing, indicating the location it was measured, which was not as important for our course. And VS30, that's what we will be talking about when we are presenting NBCC. That's an important indicator of the strength of the rock. What is the velocity on the top 30 meters or 100 feet of rock? And the code gives us different instructions, different modification factors based on the capacity of the rock on top. Normally, the better rock means faster shear wave velocity. That's shear wave velocity on the top 30 meters. Looks like this was a more competent rock because the shear wave velocity was 522 versus 350. And I think this one is distance from the main rupture. So this location was 15 kilometers away, and this location was 4 kilometers away. And these plots you see, or I see often as an earthquake engineer. What are the accelerations in different directions, in the east-west direction, north-south direction, and vertical direction? I did mention that since Kobe earthquake, we pay a lot more attention to vertical earthquake, while the primary philosophy of earthquake engineering is based on horizontal earthquake. So basically at this station, the 3 accelerations in 3 directions are recorded. These are the real recorded values. And then these 3 were changed to, or not too often, the horizontal ones. For comparison, they were changed to the response spectrum. We talked about that. Spectral acceleration, meaning the maximum response that each one of these earthquakes can create. So say east-west is probably this blue dot. North-south is this yellowish one. Black is the geomean, meaning geomean means that's a way of creating average. So you can, in a way, think about it as an average of the two responses in two directions. Now, we will see in NBCC that there are like a standard spectral plots that we use based on NBCC. And in Turkey, similarly, they have apparently TBEC, which is their standard. It was quite new, 2019. They cover two levels of earthquake. We previously talked about it, like this one you can remember, almost 2,500. That's an important number in earthquake engineering. This one you can remember as 500 years, slightly lower, both of them. So return period, typical return periods considered in earthquake engineering, and in NBCC, this 2,500-year return period is more important. And so they have done their own studies and created curves, etc. And the Turkish code was telling the engineers to design for this red one, like design the important structures for the red spectral acceleration. However, what happened in reality was the black one, which was higher, at least for very stiff structures, say about 0.5. 0.5 is not too low, it's like for a few story buildings. So the demand, the real acceleration was much higher. And that's part of what we will discuss in the philosophy of earthquake engineering and providing ductility, that while we try, or the geologists try to get the really best estimate of earthquake demand, however, earthquake is a stochastic process, it's a random process, and it might go higher. So I cannot even call it mistake, but they did a good job. Probably they used their best tool and the historic evidence, etc. They did probably a great job. Got this red curve, but in reality, earthquake engineering is about a random stochastic process. And we will see once and again the necessity that we should provide ductility, as the earthquake could easily be greater than what we designed for. So the Turkish earthquake reiterated one of the top issues in earthquake engineering, that we have estimates, but we don't have the reality. In the other station, apparently they went through the same process, and apparently their estimate of the 2,500 years return period is much greater than what happened in reality. So this is a stochastic process. They get it almost right, but it's not perfect. Or we get it almost right, it's not perfect. That's why we take advantage of ductility in the system. And that word ductility, when you get into the engineering side of earthquake engineering, we keep on repeating it. I mean, I have better repeated so many times that just sits in your understanding. So those were examples. A few more examples from other stations. Here again, for the station 4615, the demand sits well underneath the design what was provided by the code. In this station, for stiffer structures, it sits well underneath, but for like taller buildings and buildings with larger period, it was greater than the code estimate. Similarly, you can imagine that exact same scenario will happen. I don't even say may happen, it will happen in BC for the buildings that you will design. So yeah, just I shouldn't be too naive to think that I designed for the building code in BC and I am safe, because what will happen is that the demand will be greater. And I should have it as earthquake engineer in my mind. I should provide ductility. Although, yeah, we do, I mean, the geologists or the people who create National Building Code of Canada, they do a great job. And every 5 years, they review their procedures, they make it better and better. And in the past 20 years or so, better meant larger. So they have made the demands, the estimated demands larger and larger. They do a great job, but that's the fact about earthquake engineering. Moving on, some pictures from what happened to the infrastructure in Turkey in 2023. That's like a electricity line almost failed. Huge movement. I can't even believe it. I was not there. These are one of the things that people don't believe unless they see so much movement. A structure that was well designed as far as the structural engineering is concerned, but no, because the structural engineer is in charge of other secondary components as well. The structure were on the right side, a structure where even the primary members didn't work well and probably caused a lot of loss of life. The issues could go as deep as, because we are, again, say, there's other sides, like we are not material engineers, sometimes we leave it to the material. The different types of structural engineers who decide about the material used in concrete, but things can go wrong there. Aggregate gradation was not appropriate. Like you see huge gravel in there, which probably caused the damage here. And the reinforcing was unribbed, which won't happen anymore because, yeah, I only have seen unribbed reinforcement from, I don't know, 1960s, 70s. So maybe this was an older structure. Nowadays, yeah, all reinforcement they are ribbed, which means that they don't slide inside the concrete. So these issues to be aware of. Abutment rotation. So yeah, that's bridge. This bridge is sitting on the abutment, and design of the state, we said it's important. And this abutment has rotated probably because of the soil failure underneath it. But the seat, there are some requirements in the codes that for the seat length, at least they have met that. So even after some movement of abutment, the deck and the superstructure didn't fall off. So that's a good design. But however, we are seeing a lot of damages. Okay. Jumping to why earthquakes happen. And that area of knowledge is called seismology. There is, looks like, still Wagner's theory of continental drift is still considered valid. So no better theory has risen as far as the latest books that I looked at, and I pulled out those sketches from. There is a lot of evidence, and top of the list is the shape of continent, suggests that at some point in order of millions of years of history, all the continents were right by each other on one side. And yeah, for me, I think the top of the list is that those shapes match each other so well. Like this is in the center is Africa, and this is South America, and the shape of these edges match very well, which is a very good proof that this theory is a good assumption or a good theory. Not sure if it's fully proved or just general judgment, but it's a very good judgment. Again, here, other side of Africa and the corresponding side from South Asia, they also match well. And so there's a lot of indications that throughout order of millions of years, there's there was like one piece of land in a way, and they cracked and they departed from each other and created the continents. So here's the other North America. Here's where most of us live in like the top corner, Vancouver. Not top corner, but nearly halfway to top. And yeah, so earthquake engineers think or blame a lot of earthquakes on this phenomena that these continents are still changing their distances from each other, sometimes drifting away, sometimes pushing onto each other, like moving towards each other. So those movements have resulted in creation of what we call tectonic plates, meaning the plate, what we call plate, is larger than continent. So again, at the center of this picture, you can see African continent I'm pointing at. And the plate is larger than that, meaning that the plate really goes under the ocean. There's a boundary between this plate and the South American plate, which is greater than what we know as the South America continent or part of continent. And so these plates have a boundary, they push towards each other, or they move away with each other, and that causes surface earthquakes in a way. So different continents here, Arabian Peninsula and Africa push into Turkey, and that's one top reason that earthquake happened in Turkey, which is about this area. So they also cause a lot of earthquakes in Iran, where I was raised, and so that's top reason why Iran is a huge major earthquake zone, because these plates are pushing towards each other. Eurasian plate and the Arabian plate, they're really pushing to each other. And African plate is also pushing upward. That's our general knowledge. I don't know if it's 100% proven, but it's very reasonable. So that's something to agree with. And it helps us with understanding the phenomena. Jumping into this side about other region, it's this region. That's where North American plate is pushing towards the Pacific plate. And I understand that we will see the more zoomed picture in the slideshow. There are probably subplates, smaller plates in this zone that they push into each other, and they cause the major earthquakes in other regions. So this is, I think, a location of a lot of earthquakes are recorded on the planet. One more time, jumping to the previous picture. It looks like that's coincidence. There's a coincidence with the boundaries between the plates. Or maybe that's the way they recognize where the boundary is, because they saw a lot of earthquake activity here, and for scientists and geologists, that should be a boundary between two plates. And similarly, most of us should mostly focus on this area, because this is our zone of interest. In this course, we are working and living in British Columbia. Okay, another colored picture here. Africa again here, different plates shown in colored. North America here, that's top interest for us, and Pacific plate, they are pushing towards each other here. They're sliding with respect to each other here, and that causes earthquakes. Looks like there's a small plate here, which is called Juan de Fuca plate. That name should be familiar to you guys. That's probably almost the name of the sea south of Victoria. So there's a plate, major plate there, Juan de Fuca plate, pushing against the North American plate and Pacific plate. That's why we have a lot of earthquakes in this region. So the description is that Earth's outer shell is fragmented into tectonic plates. And every year, the movement could be something between 0 and say 4 inches. The plates initially strain elastically. When the stress exceeds the ultimate strength of the rock, they break and move suddenly. So say if there is a location, say there is a shear movement here, the two sides move with each other in shear, and at some point they suddenly break, and then there is a shock that we will observe at the surface. Because they initially moved together, some strain energy built up, and then when they release, then that strain energy changes to seismic waves and earthquake. There's this interesting notion of rings, a ring of fire, which means earthquake zones all around the Pacific, and we are located here, so we are part of the ring of fire. A lot of earthquakes and a lot of volcanoes are around us, around, let's say, the Pacific, around the Pacific, because of those tectonic shells. Close to us, we have noted 2 earthquake mountains, Mount St. Helens, which we know in the 80s, I think it has a minor eruption. And it looks like Mount Garibaldi is also potentially earthquake. Mount Garibaldi is probably closer to Seattle, if I'm saying right. St. Helens, yeah, I know that it's halfway between Seattle and Portland. When you fly in that direction, some pilots, they tell you, oh, look down, that's the Mount St. Helens, and you can see sometimes from one of the windows, and it's erupted on top. And there's a recent history of a minor eruption in the 1980s. So maybe next time you fly in that area from Vancouver to Portland or something, look around and try to locate it. It's a very obvious eruption, signs of it's a volcanic mountain in a way, so it's obvious. Especially if it's not a lot of clouds around, you clearly see that on the path. And a lot of times when there's good view, the pilot will also inform you that you are flying by Mount St. Helens. Again, as I said, lots of earthquakes in the Ring of Fire. 75% of volcanoes, I think it means of the world, are in this ring, and 90% of earthquakes happen here. Canada, US have experienced less destruction because, they're both new and rich, so both factors help with prevent having good buildings. So the buildings are new and they are well built, so we don't have huge concern, but we should pay attention, keep on paying attention to the new designs. Subduction earthquake, you should be familiar with that because that's a phenomenon that happens close to Victoria and Vancouver. We have a wonderful subduction zone here. And as earthquake engineers, you will hear that a lot. Basically, this is the Pacific Ocean and continental plate is here. Our cities, or even Victoria, slightly into the water, but really on continent. So at a distance away from Victoria, the continental plate and the oceanic plate, they are pushing into each other, which has resulted in the oceanic plate go underneath. So that's why we have a subduction zone. It goes underneath and it causes some earthquakes for the way that I mentioned, that they are moving and a strain energy builds up, and suddenly at a location or at a few locations, it blows up in a way and causes huge shaking. That's basically the phenomena we call subduction earthquake. At least for our region, it's the subducting plate is the oceanic one, and the top plate is the continental plate. Sudden release of friction forces develop the earthquake. And here again, a schematic picture of how in any earthquake, the two sides of like the two plates move with respect to each other. Originally, they don't really slide. Some strain energy is built up, and when they suddenly rupture, causes huge shake or minor shake, causes shake and earthquake. And yeah, you can do this practice as well. Building up, like you build up huge force and strain energy, and the friction is preventing. And then suddenly, when you release it, you release lots of energy in a way. So that's snapping the fingers. So you can have that picture in your mind as when you want to imagine how the earthquakes happen or practice it. So you apply pressure normal to your finger and thumb and apply sideways force at the same time until it breaks, and until there's a snapping in a way. And you will feel energy release by snapping. Yeah, so again, one more time, one more emphasis, our Cascadia subduction zone, where the Juan de Fueca plate, it's also called Juan de Fueca subduction. Juan de Fueca plate, that's the smaller plate that I showed to you, goes underneath the main North American plate gradually, maybe a few inches a year, and it gathers energy until it breaks and causes earthquake or even volcanoes. So here we have tried to show the process of volcanic process. This plate was solid, went further and further down until it was too hot and it started melting, and the rising magma came up the Mount St. Helens, which is close. I mean, in terms of earthquake engineering, it's close to us. So it's like halfway between Seattle and Portland, or about that region. This is called Columbia Plateau. Yeah, so that's the main phenomena here. Now some terminologies here that I should be aware of, but I should admit that I sometimes mix up these two: hypocenter versus epicenter. Epicenter is like when you are at the surface on the ground, where you will observe the earthquake will come from. Like from the surface, you will see that the earthquake is coming from here, which is called the epicenter. And that's your observation station. And the distance is epicentral distance. Remember, I showed you on those diagrams from Turkey. I said it's like 5 kilometers or 15 kilometers. That was the epicentral distance from epicenter to their recording station, the seismographs. However, the earthquake has happened really at a depth, at a location we call hypocenter, which is the real location of the breaking and earthquake, where earthquake started. The depth is focal depth, and there is a fault with fault plane with a deep angle. 3D view of the same thing on this side. As you see, the earthquake, the waves originate from the hypocenter, but from the surface point of view, it starts from epicenter. And movements could be horizontal or vertical at the fault plate. And there's this division, more of interest to seismologists: shallow earthquake, intermediate, and deep earthquakes. So for us, it's good to know that earthquakes could be as deep as 700 kilometers and still they affect us, or as shallow as 70 kilometers, 40 miles versus 500 miles. Different types of fault types. Yeah, this is also something that you should be aware of, be able to find it, but I personally can never memorize it. So normal fault types, when the two sides move away, reverse, when the two sides move towards each other, and this middle one is really reason. A straight slip, when the two sides slide horizontally with respect to each other, depending on whether, like, on each side, when you stand, like for this one, you see the other side moves to the left. For this one, in whichever side that you stand, you will see that the other side goes to your right side. So that's different naming conventions for them. And if you see those naming conventions in the report, you should be able to find it in the book or on the internet. You should be aware of the different types of fault type. Maybe it affects your design. Maybe your building is here and you want to know whether it pushes down, goes down, or pushes up, or maybe the two sides may move with respect to each other, although you really avoid building on the fault locations, but maybe there's a like water line that should pass through this, so you should be aware of whether which side will move to which direction. And yeah, so the again more terminology on this side for a straight slip, as we said, horizontal movements happen, and normal fault where you have vertical movement, or reverse fault, again vertical movement, and a combination of the two where both horizontal movement and vertical movement happens. So for certain infrastructure, you must be aware of that, because there might be like a transmission line, and I said, like transmission and distribution are hot job opportunities for you guys, and yeah, so it's very possible that the transmission line has to go over fault, and you should know the characteristics of that fault, and then you know, like, one of your towers will move to the right with respect to the other one during earthquake, and you should be able to accommodate for that. More about the characteristics of earthquakes and seismology. Different waveforms. These are important for earthquake engineer. We have two important waveforms, which is P wave and S wave. P wave is mostly axial, as if you have, for us as structural engineers, we can assume a column with axial movement. This is, for us, is as if a shear with shear movement. So while the wave is moving in this direction, the direction is shown, the movement of particles is perpendicular to the direction of the wave. For P waves, both are the same direction. There are also some surface effects, which is like love wave, when the surface moves right and left, or Rayleigh wave, where they kind of rotate. The particle movement is rotation. So the blue shows the particle direction, and the arrow shows the direction of movement of the wave. Again, a schematic of wave propagation from what we call hypocenter towards the surface. Primary or pressure is this one. Secondary or shear is this one. They are body waves. Surface waves of interest are Rayleigh wave and love wave that are shown here. Most important ones are those body waves, primary and secondary, which go from the source and hit our building. Yeah, so surface waves. I wanted to say Turkey, but this is Christchurch. So they really show the pattern that we were discussing. And yeah, so for Rayleigh waves, the pattern is something like this. It will cause hills, pseudo hills up and down. For love wave, this one looks like a love wave, so going right and left, as shown here. We are almost getting to the end of this session. Yeah, I can stop here at this picture of Christchurch, so that we remember to start right here on Friday. Yeah, tell me questions that you have about the presentation, everything. Get started for your project. Don't wait for the marks because all of them look very good. Just continue. And you have 3 weeks for about 60%, and then 2 more weeks to get into 100%. And before you get too busy with your other course projects, you have done a good job in this course. So we planned it well so that you guys learn and enjoy, not see too much pressure. Anyways, so I'm waiting for questions and comment, or just open your mic. Other than that, have a very good rest of the week. And I will talk to you guys on Friday. Again.